Welcome to One Chemistry. Always try to do your best. Now, let us see about 100 concepts in organic chemistry. We are seeing it as episode. This is the episode number 80. If you didn't watch previous episodes, I encourage you to go and see. Here, we solve 5 problems step by step. Stay tuned. Let us see the first question. They given the 3 different alkene there. First one is cyclohexane with alkene. The second one is 2-butene with trans configuration. Third one is cyclohexene with methyl group. Here they are asking reactivity of alkene in Wilkinson catalyst. Basically it's a reduction reaction. So basically you have to find which one reacts faster, which one reacts slower. So from the question of 3 different alkene and the reaction with Wilkinson catalyst, you might realize the question is really about structure versus reactivity. The answer is B. Let us see how. Here you have to look at the Wilkinson catalyst. It is a very bulky catalyst. It has many phenyl group inside. Actually it has 9 phenyl group inside and chlorine is also bulkier one. So it often reacts with very less steric situation. So the property of Wilkinson catalyst is important. It prefers cis over trans because it is nature. There is no reason for it. And it prefers less crowded. Obviously it is a bulky one. It goes for less steric position. So let us analyze the structure based on this fact. The first one is cis alkene. So definitely it will be more reactive. Second one is trans alkene. So definitely it will be less reactive. The third one will be steric. So if you compare, it is steric because of 3 methyl group and steric. So it will be least reactive. The most reactive is cis, least reactive is most steric one. So if you look at the reactivity, first will be higher, then comes second, least will be the third one. So the answer is clearly B there. Here the concepts you have to learn here is Wilkinson catalyst is bulky, always prefer less steric positions. Then let us look at the next question. The question is really about finding the non-aromatic compound. They given the 4 different compounds. First one is 7-member radical, second one is tropylium cation, third one is anion, fourth one is cyclopropene with ketone there. So basically you have 4 different structure of 4 different properties. So you have to find which one among this is non-aromatic. So the question is really about charges versus aromaticity. The answer is A. Let us see how. Here we have to analyze each category separately. So let us take A there. A is the radical one, so it's often considered as not aromatic because radical is chargeless, so the conjugation is questionable, so it is considered as non-aromatic. So it will be our answer. Let us eliminate other 3. The B is cation. It is 6 pi electron, unconjugated, unplanar. It is aromatic. If you look at the C, it's 8 pi electron, conjugated, planar. So definitely it's anti-aromatic. If you look at the D, people often confuse is aromatic or not. It is aromatic because the positive charge on carbon, which is partial positive charge due to oxygen electronegativity, it creates the conjugation. So it is conjugated and planar and 2 pi, hence it is aromatic. Here partial charge provides the conjugation, the space for the conjugation. So our answer is clearly A, which is radical anti-aromatic one. Here the important concept we have to learn here is radical is non-aromatic and the partial charge also provides space for the conjugation. Then let us look at the next question. The starting middle is cyclohexane, which is containing epoxide and tertiary butyl group. Epoxide is above the plane, tertiary butyl group is above the plane, hydrogens are below the plane. You are reacting it with sodium acide. They ask you to find the product. The products are 4 different ones. All are differ in the stereochemistry and the position of OH. Basically we are playing between OH and N3. It can be differs and its stereochemistry can be differs there. So from the question of epoxide and reacting with sodium acide, you might realize the question is really about regioselective ring opening. The answer is D. Let us see how. Here epoxide is there, you are reacting with acid. Basically you are opening the ring. Before we get into the reaction, we have to realize what is the structure is really about. If you convert it into chair position, the tertiary butyl and epoxide is syn to each other. The epoxide should be syn, So one bond should be axial, one bond should be equatorial, and the important thing is both should be syn to the tertiary butyl group. Here our N3 reaction require axial position, so only axial position is free at the third position, not at the fourth position. So only axial is free there. So N3 attack ring is opening. You have the N3 near to tertiary butyl and OH is away from there. So if you draw nicely in 2 dimensions, the answer is D. OH and N3 are trans to each other, where the tertiary butyl group is on above the plane. Here the concepts you have to learn here is epoxide require axial and equatorial position because it form syn kind of bonding. SN2 reaction require backside attack, so where the axial position is free, SN2 happen. Then let us look at the next question. Starting middle is ketone with side chain amine, which is tertiary amine. You are reacting with methyl iodide and sodium bicarbonate and methanol. They ask you to find the product. The products are like methylation as well as the elimination. The A1 is with methylation at alpha position, B1 is methylation at oxygen, C1 is like replacement of ethyl group, the D1 is the elimination reaction, simple elimination. So from the question of amine and the competition between elimination and substitution, you might realize the question is really about regioselective elimination or the substitution. The answer is D. Let us see how. Here the starting metal is amine. They are reacting with methyl iodide. Methyl iodide CH3 possesses the positive charge, so it readily acquires the nitrogen lone pair. Here CH3 occurs readily available nitrogen, so it forms quaternary ammonium salt. The quaternary ammonium salt is a good leaving group, so it needs little bit push. So what really happens is hydrogen leaves. The quaternary amine also leave. You have alkene, which is terminal alkene. This mechanism is known as Hofmann elimination. Less substitute product is favored here. So the answer is clearly D. Let us eliminate the other 3 possibilities. The first one, the substitution happened at methyl. So it needs strong base because it removes the alpha proton. The same thing with second one, which also have base alpha proton. So removal of enolate formation also not possible. So it needs strong base. The fourth one is C2H5 is removed. C2H5 is a not good leaving group, so the reaction is impossible. Let us see the next question. The starting metal is acid attached with 5-member alkene, which have further side chain ketone. The product is amine. The acid converted into amine. They ask you to find the reagent. The reagents are lithium aluminum hydride, or hydrogen in palladium carbon, or phosphine with water, or lithium in liquid ammonia. 4 different reagents. You have to know the reactivity and selectivity here. So from the question of starting material and regioselective reduction, you might realize the question is really about special reagent and naming reaction. The answer is C. Let us see how. Here you are converting acid to amine. It's a very famous reaction. It is called Staudinger reaction. It converts N3 to amine. The mechanism is very complex. You have to study separately. So C is our answer. You can answer this by elimination mechanism also, because palladium hydrogen reduces the alkene, so it is not selective. Lithium aluminum hydride reduces the carbonyl, it is also not selective. Lithium and liquid ammonia reduce the conjugated double bond, so it is also not selective. So our answer is clearly C there. Here the concepts you have to learn here is Staudinger reaction, which converts acid into unusual amine. That's all from this episode. I hope it was easy. Thanks for watching. If you have any suggestion, comment below.